All right, let's get right into it. Today, we're going microscopic to explore the incredible engineering of our cardiovascular system. We're talking histology, the actual cellular architecture of the heart and the blood vessels. And look, this is absolutely essential stuff if you want to understand how this system really works and, what happens when it breaks down. So let's frame this whole explainer around one big question. How does the microscopic design dictate function? Because I'm telling you, from the massive aorta all the way down to the tiniest capillary, every single structural detail is there for a reason. Once you understand this blueprint, the whole system just clicks into place. So, where do we even begin? Well, we start with the foundational blueprint. At their very core, you can pretty much think of all blood vessels as just a tube, a simple tube. But it's the specific and frankly brilliant design of that tube's wall that makes all the difference in the world. And those walls, they are almost always built from three distinct layers, or as they're called, tunics. Just think of this as the basic architectural plan for the body's entire vascular plumbing system. So let's break down what each of these layers does, and you'll really see how it all comes together. Okay, so let's build a blood vessel, starting from the inside where the blood is actually flowing, and work our way out. First up, you've got the tunica intima. This is an incredibly smooth, slick inner lining that makes your blood just glides right on through with almost no friction. Right outside of that is the real powerhouse layer, the tunica media. This one is packed with smooth muscle and elastic fibers. And then, wrapping the entire thing up is the tunica adventitia, which is this tough, fibrous outer coat that kind of anchors the vessel in place. So, now that we have that three-layer blueprint in our heads, let's see how it gets modified for different jobs. First on the list, arteries. Okay, these are the big guns, carrying blood away from the heart, and they are built tough. They have to be, to withstand that massive pressure wave from every single heartbeat. And the secret to their strength? It's all in the tunica media. This middle layer, as you can see here, is super thick and muscular in arteries. That's what gives them the power to absorb the shock of that heartbeat and then use that elastic recoil to push the blood forward. It's this tough, robust structure that lets arteries keep that nice, perfectly round shape you see when you slice them in cross-section. Okay, now let's flip over to the other side of the circuit. If arteries are built for pressure, veins are all about handling volume. They're the low-pressure return system, and they act as the body's flexible blood reservoirs. That's why we call them capacitance vessels. And this is just a fantastic example of structure meeting function. Veins have much thinner, kind of floppy walls and way bigger internal lumens so they can hold a lot more blood. Their thickest layer isn't the muscle, but the outer tunica adventitia, which just provides support. And because the pressure is so darn low, they need these little one-way valves to keep gravity from pulling blood back down. It's this less rigid design that makes them look kind of collapsed or squished on a histology slide. So this slide right here, this is your ultimate cheat sheet. Seriously. If you're ever looking at a slide and you have to tell an artery from a vein, this is everything you need. Thick, muscular wall, nice and round, that's an artery. Thin wall, weird collapse shape, maybe you see a valve, you're looking at a vein. It's a classic spot test. All right, we've covered the plumbing. Now it's time to head into the engine room, the heart itself. I mean, this is the most specialized, powerful muscular pump you can imagine, and its wall has a completely unique histological structure all its own. Just like the blood vessels, the heart wall has three layers. On the inside, you've got the endocardium, which is actually continuous with the tunica intima of the big vessels. On the outside is the epicardium, and that's where you'll find those critical coronary arteries. But the absolute star of the show, the main event, is the myocardium. This is the thick, powerful cardiac muscle that does all the work. Now, if we zoom way into the myocardium, we see some amazing stuff. The muscle fibers themselves are branched, and they're all connected by these special junctions called intercalated discs. Now, these discs are the secret sauce. They literally lock the cells together and let electrical signals flash between them instantly. This forces the entire muscle to contract as one single, perfectly timed unit, what we call a functional syncytium. It's not just a pile of cells, it's a team working in perfect unison. But what's really fascinating is that not all of the heart muscle cells are there to pump. The heart has its own internal, high-speed electrical wiring system, and it's made of specialized cells called Purkinje fibers. And you can actually spot them on a slide. The worker cells that do the contracting, they're smaller and stain darker. But the Purkinje conduction fibers, they're much bigger and paler because they're packed with glycogen for energy. Their only job is to move that electrical signal as fast as humanly possible. Okay, let's start to wrap this up by pulling together a few final super high yield points. These are things you absolutely have to know to understand how the heart is really put together. First up is the cardiac skeleton. Now, this isn't made of bone or anything. It's a tough, fibrous framework deep inside the heart. It does two critical jobs. One, it's the anchor point for all the heart valves, giving them something solid to attach to. And two, it acts as an electrical firewall, stopping the atria's contraction signal from spilling down into the ventricles before it's supposed to. It's the foundation for both the heart's mechanical and electrical integrity. And look, if you need just one number, one statistic to truly appreciate the heart's insane work ethic, this is it. A full quarter, 25% of a heart muscle cell's volume is made up of mitochondria. Those are the little power plants of the cell. This is what fuels every single beat, every second of your life. And it's exactly why the heart is so incredibly dependent on a constant supply of oxygen, which makes it so vulnerable to ischemia. So we're going to end with a challenge. Now that you can see this amazing link between the tiniest structures and the biggest functions, start thinking like a clinician. What happens when these structures fail? What pathologies could you predict? For instance, what happens if that smooth tunica intima gets damaged over and over again? Well, that's the very first step in atherosclerosis, the hardening of the arteries. See? Understanding this microscopic blueprint, that is the key to diagnosing and, one day, treating cardiovascular disease.